吗？有。Okay, how? So today, before I start with the lectures of light, I would like to show you very good resources for free textbooks. 今天在开始讲近代物理以前，我从今天开始要讲近代物理。我想要先给大家看一个，趁现在可以赶快下载很多很棒的教科书的网址。You can enter. This is provided by a European publisher, Springer Verlag. I think it is a big group of publishers, and they have a very big headquarters in Germany, and they have another quarter in England. And I like the German publisher very much because they invited all the professors in the university and asked them to write textbooks by themselves. And I really think the quality of their textbook is very, very, very good. It's like it's like the teachers really combined the knowledges and their experiences in researches together and giving the textbook like their collection of experiences. And usually the explanation is much deeper. So I like those textbooks which is originally written in German and then translated into English, and that is really, really good. And now because of the coronavirus, and you know that in Europe and in USA, and it's just a lockdown and all the people should stay at home, they are not able to go to school. So now many publishers, they just put all of these textbooks online for free. So now you can download it. And here are so many good textbooks that I find here. I just look at the categories of physics and mathematics, and I find them really, really good. And you can find some engineering textbooks and programming textbooks too. So this is a very good opportunity for you. If you buy the book with a hard copy, with a hard cover, and usually it takes something like $6,000 to $9,000 Taiwanese dollars to buy a book like that. So usually we are not able to afford a book like that, and then we go to the library to borrow it, study it, and give it back. But now you have the chance to download the electronic version. So please take this chance and then download the books that you need. 这边给大家看一个我觉得非常棒的机会。现在因为那个武汉肺炎的关系，所以在美国跟欧洲那边的状况是比我们更严重的，所以他们的整个那个大学是全部关起来，就是教室不能去，不能上课，然后也不可以去实验室，就是他们已经是完全停摆状态。那这个时候有很多欧洲的出版商，然后他们就开放教科书啦，还有一些论文、经典论文是可以免费下载的。然后像这些教科书，你如果去买一个精装本的话，台币多啊，5、6千块，甚至7、8千块、9千块都有可能。对，那如果你现在可以免费下载电子版本的话，那么就是真的是非常非常的非常佛心，然后非常有帮助。我自己是非常喜欢 Springer Verlag， 就是 Springer 出版社这家公司。其实我不确定它的总部是在英国还是在德国，但是至少我知道他们在德国有一个非常大的出版中心。然后我觉得这家它的特色就是呢，其实也跟德国的学术环境有关系。就是德国那边，他们对于一个教授的学术上的表现评断的标准是你能不能够写出一本教科书。就是以你自己的专业写出一本教科书，不是像台湾这边，你就是那种期刊杂志上面短文3、5页，就是德国人不太看那种东西，他们会要求教授一定要写教科书。那造成的结果就是德国有很多非常好的教科书。那虽然他们一开始是德文写的，但是通常出版社会再叫翻译师来把它翻译成英文版本的。那我非常喜欢这种从 德文翻译成英文版本的教科书。因为你去看它里面的内容的时候，你就会发现他们对于很多，比方说对于物理现象有很多嘛，然后那你物理现象整理起来以后，那个分门别类，你会发现它真的分得比较好。然后或者是他在描述一个物理现象，你要怎么样去思考它，然后你会发现，他思考的真的比较深，然后他对于一些似是而非的地方的解释都会非常非常的清楚。所以我自己在备課的时候，其实我都是在看我以前在德国念书的时候留下来的笔记，然后还有我那个时候留下来的一些教科书影印本。对，那我非常推荐大家赶快趁这个机会去下载，对，因为这样子很省钱，而且以后你不管是到高年级应该还可以用，甚至我觉得主要的帮助应该是会在你进入实验室开始做研究之后，因为它有很多工具书，然后呢，它在一些专门的类科的时候，它都会放1-2本那种 introductory， 就是介绍型的书。所以你赶快趁现在，就是看你对于什么领域有兴趣，你可以赶快把这些很优质的教科书下载下来。So this is your chance to download nice textbooks for yourself. For example, I just look at the category in physics. Here are a lot of categories. You have computer science, engineering, physics, mathematics, business and management, and here are some other tools, like here are many statistical theory, programming techniques, and here are some others like mathematical methods in physics. This is so important for me. And for example, physics, if I click in, and here are, this is for senior students, and like this quantum mechanics for pedestrians, 这个是给路人的物理的量子力学。可是I just click inside and I just look through the books, and this is not for pedestrians, and this is for the university student in the first or the second year. So you can use a simple calculus, but he just teaches you the central concepts of quantum mechanics. These two books are really, really good. And this one, Oscillations and Waves, it's just a reminder for you. When we are starting the physics in university, usually we start from Newton's point of view. So we started everything with particles, how particle moves, how particles, the velocity, the acceleration, rotations, and all of these things. But there are another perspective provided by Hooke, but somehow we didn't look at it at all, isn't it? And this is the book about the perspective from the other side. If we start everything from oscillations and wave, and how do we look at our physics that way? So I think this is really, really good. 大家应该会注意到我们的大学物理我们一开始的时候，我们就是直接就站在牛顿的旁边，然后顺着牛顿的眼睛看，然后我们就会说，我们都是粒子嘛，那粒子停在那里，粒子开始跑了，速度是多少？粒子受力加速的加速度是多少？我们的想法就是一直跟着牛顿跑。可是其实有另外一个视角的部分呢，我们几乎没有真的站在那个人的眼光看待过这些事情。那个人就是胡克，就是胡克的震荡跟波动力学。对，我们的基本物理从来没有从那个方向开始讲过。那这本书呢，就是从那个方向开始讲的，所以我觉得这个真的是蛮不错的。And here are linear algebra, analytic geometry. This is just the basics for everything. And symmetry, this is good, but this is for my own work. Astronomy, electromagnetism. This is the classic problems in classical electromagnetism. So you can take it and then you can just look at it and then you can see how mathematicians solve the boundary problems. Here are many things. And in the category of math, sorry, I'll just go back. Mathematics. This is very good too. So here are linear algebra, important for you for everything. And partial differential equations. This is good, and you can download it. Linear algebra. And partial differential equations. Linear algebra and partial differential equations. These two are the must-have tools to analyze any kinds of problems. And modeling if you need it, and then you can see how the logic of modeling works. Here are calculus and geometry, calculus, Fourier analysis. This is the third important topics. Probability theory. Yeah, this is very important too. So here are many good books for you to download. And for the applications, I think you are much more familiar in programming than me, so you can just look through the list by yourself. Here are the mathematical methods in physics. I just remember I saw a book like a dictionary, but it's the dictionary of equations. Sorry. Data analysis. This is important too. Data analysis, especially if you're working in industry, and all of the data is statistic, because you're working with products, and products is something like you have a big matrix, you have a big amount of something, and you have to analyze the distribution of some characteristic, and then you have to set up the criteria, which is good, which is bad, and what about the yield, what about the back rate, things like that, and you need the knowledge in data analysis. And Python, MATLAB, here are the must-haves. Yeah. So, okay. So you can just here. This is just showing you the web page again. Somehow I cannot find it by Google, so maybe you should just take the link and remember it. So this is really good. 我觉得这间出版商真的蛮好心的，因为他把很多我们在实务工作上面一定会用到的工具书，他就是把它整本的电子版都放在网络上让你下载，所以就非常推荐大家趁这个机会赶快下载。虽然我觉得我下载后我还是会去买精装的啦，因为我觉得有一本书可以这样翻，在我工作的时候我觉得比较方便。好，我把这个放在这边20秒，你可以记录，然后回去慢慢选择你喜欢的书。好，那么我就收起来咯，收起来，不存。那我这边 tab 我全部都关掉。好，有在直播中了。那么我们就开始上课。Then we start our lecture. So now we are with light. So light. Here I will introduce light from the point of view of a point and from the point of view of waves. So I am sure everybody knows that the light has a particle-wave duality. But before we go to the section about duality, we have to have a review about the particle and the wave. And we have to apply those analytical models on light, and we can see the the good points, and we can see the weakness of these two models on light. 所以我们现在我们的近代物理，我们从光学开始讲。那光学，我想大家应该都已经朗朗上口，就是光有波粒二象性。但是呢，我觉得我们先来检查一次，就所谓的波跟粒，其实是波动跟粒子两种模型。那我们会用这两种模型去套用我们看到的各种物理现象。那你把波跟粒子两种思考模式硬套到光上面的时候呢，你就会发现这两种模型它各自有它们各自的强项，但是它们也各自有各自的缺点，或者是限制，应该说限制。所以你在波粒二象性这个题目上面呢，你就会看到，粒子跟波这两种思考模式，它们各自的立足点跟它的局限在哪里？那我们今天我们讲光学的时候，我们从这个方向切入。So we get into light, the topic of light from this perspective, and here is a summary of the properties of light. So let's just leave the electronics behind, and then we just get back to Maxwell equations, and we just finished the derivation of wave functions of radiations, and then we compare the wave equations to some observations on light. And here are the properties of light which has been discovered by various experimental physicists, and through maybe 200 or 400 years. Okay, and here is the list of all of these properties. 所以呢，光学到底是谁或是什么时候开始研究的，其实真的太久远了，大家已经不记得了。但是呢，这边我列出了几个光的特性，然后这个是至少人类在科学史上面有找到一个明确的发现者，或是大家会觉得这个特性或特质很有趣的，那我们这边把它列出来。So this is the first thing is light is always walking in a straight line. If you don't change the media, if you just leave it in air, and then we always see the light is walking in a straight path. And this is already known. And here is, and the second is the reflection. This is very obvious and known as well. And then this is refraction. Refraction happens when the media is changing. For example, the light is going in a straight line, and first it passes a thick layer of air, and then it goes into a thick layer of plastic. Air and plastic, they are different medias, and then you can see the direction of the light just moves. Somehow it turns in another direction. It keeps a straight line, but it turns in an angle like that. And that is refraction, 就是折射。And refraction was analyzed, or we should say modeled, by Snell in 1621. 所以这个光在跨越不同的介质的时候，会转一个角度的这个现象是 Snell 他分析这件事情，而且他为这件事情建立了一个数学模型。然后那个数学是基于三角函数的，所以就是折射率是Snell 定律。好，这个是大家都非常非常清楚的事情。然后再来是 diffraction, and then this is diffraction. This is discovered by or named by an Italian experimentalist, Italian astronomer actually. Now, what exactly is diffraction? And it's very hard to say it just by a word, so I'm going to introduce it later. 绕射这件事情你其实你很难用一个字你就知道它是什么意思。所以我们等一下我们看图之后，我们来看图，我跟你解释什么是绕射。And then colors of the light, and the colors of the light is that was I'm not sure if it's discovered by Newton, but Newton developed a systematic method to separate the light with different colors, and then he proved that all of these separated light, they are individual. So that is done by Newton. And finally, interference. Interference and diffraction are actually very similar to each other. They are, and to me, actually, they are basically the same thing, but they work on different kind of objects. But okay, and interference was, I don't think it's a discovery, but it's analyzed by Young. 就是 interference 就是干涉。那我会觉得，其实绕射跟干涉，它们其实是同一个现象啦，就是它们作用的，就是它们会发生的场合不一样，应该要这样说。然后呢，也是一样，有系统化的在分析干涉这件事情的是杨氏，这就是它是有一个那个叫什么杨氏模型还是之类的，我不太清楚。对，那么就是大概是这样。好 ，and then I think it's better if I use this slide. Okay, and all of these properties can be explained by you can explain it by thinking about light as a particle, or even explain it by thinking about light as a wave. But now we have to do a comparison. So about the light walking a straight path, particle and wave, all of them can walk in a straight line, right? So this is okay. And reflection, if it's a particle, if it's a wave, and both of them have the property of reflection, so it's okay. And then for the reflection, in the years of Newton and Huygens, they don't have the mathematics to explain it, so that was a really big misery at the time. But Newton somehow explained it by the speed of light. He just said that light is particle, and the particles are moving at different speed in different media, so solve it. So he can just explain that, that is because that is particle, and particle is walking at different speed in different media, so that caused the reflection. And for Huygens, he somehow, 6 years later, and Huygens just used the wave models, and then he can explain it by the speed of wave too. So the big misery was solved by two scientists with two different models. Okay, so we will explain it later. And then here comes the diffraction. And diffraction is the thing that it doesn't happen if light is a particle, but it can happen if light is a wave. So that was a very critical, very crucial decision here. 然后这边是特别讲一下的是绕射这个现象。如果光是粒子的话呢，就不会有绕射。所以这件事情是有点决定性的，然后对于粒子说造成了巨大的伤害。好，然后呢，再来是如果光确实是波的话，那绕射这件事情就很有可能就是一定会发生。对呢，所以就是绕射这个现象它是有点决定性的，你就会看出来说所以如果我觉得光是 particle 的话，它在绕射这个地方它完全无用武之地，就是没有办法解释。这个就是 particle 模型的极限了。Then colors. So colors, and it can be explained by light as particle with different masses. So this is possible, and Newton can explain it, and he just demonstrated the dispersion 色散 of light. So that works. And for the wave model, that remains a really big misery for the wave model, and that was the major weakness of the wave model. And then it was long later, Planck just solved this problem by black body radiation. Yeah, I will explain it maybe 2 weeks later. 好，关于光的颜色， 所以那个时候是完全是大论战，就是其实在牛顿的时代，颜色 wave light 这里要打一个叉，就是他们没有办法用光是波动这件事情去解释说光为什么会有7个颜色会分开啊，这好奇怪哦。因为波它是一个有连续性的 model，wave is a model with continuous. It's like the length of your wave can be very short, very long, and from short and long, there is a continuous changing. It's not like I have the wavelength of such a wavelength, and the second choice is 2 times of that such length, and 4 and 3 and 4 and 5. That doesn't exist in wave model. So that was a really big constraint on the wave model for light. But then when Planck somehow explained the black body radiation in a quantum point of view, and then people started to realize that so even if I use the wave model, and I can still think about the wave as the wavelength is in packages. So that was a big discovery. And finally, this is interference. And again, if light is a particle, then interference doesn't work. But if light is a wave, then interference will work. Okay, so this is the comparison of the particle and wave properties of light. And here, this is a detailed explanation about light as particles. And this is mainly centered in, we should say that Newton is centered in this school. 就是这个学派，我用一个非常人文领域的讲法来讲这件事情好了。就光这件事情，它到底是 particle 还是波，其实是分裂成2个学派。那所谓的学派就是呢，这两个学派，他们抱持的某一种信念或是某一种中心思想，都是没有很深的理论根据，但是他们就是一群人聚集在一起，然后他们就决定要拥护这样子的信念。所以这个是 light as particle， 是光是粒子，那时候就是有一群人这样子想，然后这个是以牛顿为中心人物的一个学派。So, and this is how Newton think about everything. He just tried to assign mass to everything, inertia to every rotation object, and then we start to analyze the velocity, acceleration, force, and momentum, and collision, and conservation laws, and so on and on and on. So this is how Newton is thinking about everything, and he is working on things which is moving around, speeding up and speeding down. So he would like to use this kind of thinking logic on light. So light is moving in a straight line, so he just thinks that okay, this is just like a particle moving in a very fast speed, and the path is a straight line. Then the question is, if this is particles, somebody just asked Newton, if the particle is walking this way and the other particle is walking away this way, and if they collide, and then it's just scatter, isn't it? But we never see this kind of thing in light, so what do you think? So that was a really big problem with models of light as particles. 所以那他现在就有人会问他说，那如果我们的光是一群 particle 一团，然后有一团这样冲过来，然后有另外一团这样冲过去，那他们相撞的话怎么办啊？相撞之后它不就砰，然后要么就是炸开吗？要不然就是散射吗？可是为什么我们把2束光，一束这样过去，另外一束这样过去，光好像没有发生过2束 smash 然后炸开的现象，是吧？那这个时候该怎么办呢？然后牛顿就放着不管了。So that was about the collision and scattering of light. And you do not see the scattering from the crystal light beams. So this is the weakness of the particle model. And here the second evidence. This is about the reflection. So the light, when the light is walking this way, it touches somehow a surface and then it gets reflected. And then you can see here is the angle and the other angle, and here the two angles are equal to each other. So this is just like the collisions of the particle on a hard object. And then actually you can analyze it with a model of conservation of energy and conservation of momentum. So this is a really important proof that we can work on light as they are particles. 那再来，牛顿他抓的最紧的想法就是的证据，应该说证据。牛顿他抓的最紧的证据，一个就是光会反射。然后呢，光的反射，因为它的角度，就是你进去的角度跟出来的角度是一样的。然后呢，你其实是可以套用那个，如果大家记得碰撞的话，那碰撞你一定会去分析说你的能量有没有守恒，你的动量有没有守恒。那这些所谓的能量、动量守恒，在光上面也都是适用的。所以那牛顿他就抓这个证据抓得很紧，他觉得说，因为他们有这些守恒的特性，那我认为它是 particle。好，所以呢，这个就是 people stick with what they invented。好 ，and then this is refraction that was explained by the speed of a particle. Newton just said that, it's walking in a faster speed when it's in air, and when it's getting into water or glasses, the speed of the particle just gets slower in one of the direction, and that's the reason why we have the refraction. And then he just analyzed the Snell's law and then used the energy conservation, momentum conservation, and then done. So that is, this is how he applied the particle model on light. And we're still using this thinking model nowadays. 就是他现在这种想法，我们到现在还在用。就是我们在分析古典光学的时候，或者是不是跟量子现象无关的状况的时候，我们还会再继续用这些牛顿力学的想法去分析光的反射跟折射。And here comes another question. If you are very observant, and if you are looking at the light, it's like light is going into, it crosses the border and get into the other media. But here is a part of that light get reflected. So if we are very, very strict, we just say that here is only one particle. And one particle is walking this way. How can it separate it into two parts and one part go into the media, the other part get reflected? Because the particle model is based on a thought that the particle is the smallest unit, it's not dividable. So, or we get into another dilemma. So that is really big cut on the particle model for developed by Newton. 所以，但是一些观察力很敏锐的人，他在看光学实验的时候就觉得不太对劲，因为那个光它过来的时候，确实是有一部分的光透过折射，然后就穿过去了。然后，但是有另外一部分的光是会反射的。那假设说现在有一个非常非常挑剔的人。他认为说，我现在就是控制，我只有一颗 particle 跑过来，但是，这颗 particle 为什么会在这个场合分裂成两个部分，一部分穿过去，另外一部分弹回去呢？这不就跟 particle model 的先验条件、先决条件抵触了吗？因为 particle 的先决条件就是他认为所谓的一个 particle 就是所有事物的最基本单元不可分割，所以呢，哇，怎么办？就两个想法就两难了嘛？怎么会这样子呢？所以这个是光的粒子说一个非常非常大的弱点，对，这里就弱掉了，就没有办法解释为什么事情会这样子。好。然后 and then this is the fourth evidence. dispersion. But because this evidence and the explanation of dispersion is so successful, so people stick with this explanation for a really, really long time, and we try to ignore this one, we try to ignore this one, we try to just use the classical model for the light. Okay, and here we just watch a short video and we see how Newton is proving his theory for dispersion. 我们这边看一个小小 It's revolutionary. 我其实不太确定这样子的实验在那时候算不算是革命性的？因为我刚刚听他讲话，我想到哥白尼，就是为什么哥白尼会被抓去烧死，可是牛顿并没有呢？Okay, so I'm not sure if it's a problem about the religion, because he just said that in that time they just thought that everything from heaven is just perfect, just like a perfect particle. Just a particle is for white light. And in Newton's experiment, he somehow proved that no, the white light that you see is a mixture of many different particles with different colors. Yeah, so I think that is an experiment about separating the portions in the light, and he just developed a experiment to prove it. Okay. 好。最好，以我们现代人的角度去看那时候的事情，都会觉得有一点点，对我现在其实是有一点错乱，我不太确定这算不算是一个很巨大的革命性的想法，好吧？所以牛顿他做的事情呢，就是在那个时候人的观念，他觉得白色的光洒下来，那一颗一颗都是完美的 particle。对，但是那牛顿的实验，他就说，不是。你看，我做了一个实验，我把光分开，就好像你把一堆红豆、绿豆、黄豆混在一起的不知道什么东西，你一颗一颗把它剪开，然后就是绿豆一堆，红豆一堆，黄豆一堆那种感觉。他做的实验是有点类似像这样子。好，所以呢，他就用了色散实验，然后呢，他就觉得说，我可以把白色的光再分解成更基本的不同颜色的粒子。And so he just said that white light is a mixture of colored particles. And he just used his thought of the second Newton's law. He just said that the colored particles are with different masses. And then he can apply his theories on the velocity, acceleration, and then he can start to analyze the speed of different particles, and he can just predict the refraction angle. Okay, so that was about dispersion. Okay, and now we are going to look at the same thing, but we are looking at it from another perspective. 然后我们现在要从另外一个观点来看看这件事情。然后呢，这个观点其实是从补课开始的，但是我们先看一下一个影片，因为我们其实，在物理课里面，我们对于流体，我们对于水的了解其实很少，所以你突然之间跳到波动拉姆的话，可能会觉得适应不良，所以我们先看一个实验影片。先从水开始看起。Let's just explain it first. Sorry. And this is a water tank. So I think the tank is somewhere. There is a recorder, a camera, which is recording all of these images. But this is a lot of water, as you can see. And here is a big movable plate. And the plate is pushing the water, making the water doing some oscillations。那所以这是一个很巨大的水槽，然后水槽的另外一边它有一个活动式的板子，然后那个板子你就这样推，这样推，这样推，然后你就可以在水槽里面制造出一些波，这样子。然后呢，你看到的 so the light part, the light fringes that you see is the top peak of the wave, and the dark fringes in the picture is the valley of the wave. 那亮的地方是波峰，暗的地方是波谷，然后你是从上面往下看，再看你的 water tank。然后呢，它的实验 and here's how the experiment go. So we put some plates, or we put some curved plates, or we drill some holes here, and then we try to see how wave is propagating in the water tank. So you can see that reflection, focusing by a lens. You can see diffraction and you can see interference. Stop here for a while. Diffraction. This is how diffraction works. So you can see that all of them are water, and we have something like a wall here, and we have another wall here, and here is a slit on the wall, and our pusher, the movable plate that drives our wave walking, is still here. And it's still creating the planar wave, if you remember. This is how planar wave works. It's like a plane and it's walking that way. So the planar wave is walking from here to here, and this is the wave front. The wave front is a vertical straight line in this kind of cases. But somehow, when the planar wave is passing through a slit like that, the planar wave is not walking straight like this. The planar wave somehow transforms into another shape. It turns into a circular wavefront, and the circular wavefront, they are concentric, and somehow the planar wave is converted into a spherical wave. So this is diffraction. 那绕射。这个是大家通常一看到绕射就会脑袋一片空白，但是绕射其实就是这个现象。大家可以先回想一下，我们在讲波动的时候有介绍说有平面波有球面波，对不对？那平面波就是你的波动是你的波前它是一条直线，然后呢它波峰波谷都是一条直线一条直线一条直线，然后呢它行进的方向是垂直于那个平面波的波前，这样传播过去。那现在呢，是我们用那个隔板在水里面，我们在这里创造出来的是平面波，但是平面波在遇到了一堵墙，然后想要从那个狭缝穿过去的时候，那个平面波没有办法保持它原本的形状，就是它并不会是一个平面波，然后被挡住的地方就消失，然后就是继续以一个平面波的形态往前进。波并不是这样子走的。在遇到这样子的状况的时候呢，我们的平面波会自动自发的转变成球面波，然后呢，从那个 slit 过去之后，它会以球面波的形式，然后是同心圆这样子，然后继续往前用球面波的方法传播。所以这个状况，这种现象就是绕射。那为什么在中文里面叫绕射？ defract 好像字根是从意大利文来的，我不知道意大利文 defract 本来是什么意思。那中文的翻译就把它翻译成绕，因为你看波钱的话，你会觉得那个波钱好像这样绕了一圈，这样绕出去，这样绕一圈绕出去。但是反而绕这个字造成了大家的，反而造成他的困惑，应该是这样，就是大家就绕是什么意思？对，那我觉得其实你从图像上面来看的话，它就是一个从平面波想要从一个小缝硬挤出去，然后它的应对方法就是它会把自己转变成一个球面波，然后用圆形的方法继续往前传播。好，所以这是 diffraction， 在水里面的 diffraction， 这个现象是以胡克啦，以惠更斯那个年代的人，他们常常在水里面看到这种东西，所以他看到这个时候，他不会很惊讶，然后他反而是在光看到一样的现象的时候，他就觉得我觉得光应该是波光，应该会绕射。好 ，So in the time of Hooke and in the time of Huygens, they see this kind of thing very, very often. So they just see that kind of thing on the oceans or on the water, on the river, or on any kind of water tank. And when they are working with the microscope and telescope, and they somehow discover that, light is behaving like that too. So they start to think that, I think it's more probable that light should be a wave, just like water wave. And this is the famous double slit interference. So this is the wall is like this up to here. Here's another little wall. You are not able to see it in the picture anymore, but here's another little wall. And here's the third wall. And we have one slit, the second slit. And here we are generating plane waves, and it's a little bit disturbed by the reflected light, by the reflected water wave. But that was originally a plane wave, and when the plane wave is passing through two slits, you can see that they convert themselves into two spherical waves, and the two spherical waves, they start to have constructive interference and destructive interference. So you can think about the picture, and you can have the picture of interference in your head. 所以这就是所谓的非常著名的双狭缝实验。那么你就会看到我们刚刚已经解释过的一个现象。我在这里呢，我制造出很多平面波，然后呢，我强迫这两个平面波从两条狭缝那边挤出去，然后你就会发现平面波它自动自发的就把它自己转换成两颗球面波。然后这个球面波它就是会以球面波的形式一直往前传递嘛，那么那个波峰跟波峰加起来就会变成建设性的，你的波就会变得更高。那如果是波谷加波谷，然后那个波就是会变得更深。如果刚好一个波峰跟波谷遇到，就消失就不见。对，那这个就是所谓的干涉现象。干涉现象也是他们很早，他们就在水里面就已经看到了。所以当他们做实验的时候，看到光也会这样子的时候，他们其实心情是很激动的。就那时候的人，他就会觉得说，哇，所以其实光是波耶，光不是粒子呢。因为你可以想象 you can think about if this is a particle and you're shooting a particle through a slit, somehow it's the only if the particle is smaller than your slit and then it just passes through, it doesn't create a pattern like that, or it just destroys the slit. So that is why they think that they should use the wave model to think about light. linear interference. This is 2-point forces. And you can see the spherical wavefront, and you can see how they interfere. And this is the Doppler effect.这是杜普勒效应。好 ，OK. So I hope the video like this can help you to have a very actual picture about the wave and how the wave propagates. And actually, people, I just mentioned it when we were watching your videos, and people just think about the water tank like this because they were, for example, like Hooke and Huygens, and they were looking for Saturn in the time. 就在那个时候，这件事情会浮现出来，是一个从完全不相干的事情冒出来的。就是那时候的人，他们很流行去寻找土星。就那时候人很想要看土星，然后发现土星有一个那个游泳圈，对，那他们就是非常认真的在发展各种望远镜的技术，想要看到土星环到底有几条。所以那个时候呢，他们花了很多时间在精进自己制造望远镜的技术。So that was a really hot topic in that time, and people were looking for Saturn, and they somehow, by the images, they just thought that the Saturn is not like a ball. Somehow the shape is so strange. Seems like they have some ring. It has some rings around it, so they would like to look at the rings, and they spent a lot of time and a lot of effort on improving their telescope. And the telescope was made of lenses. So here are lenses made of glasses, and they are characterizing, they are analyzing the performance of the lenses. So this is the reason why they discovered the diffraction. So they somehow discovered that no matter how perfect the glass is, or no matter how perfect the curvature of the lens are, and no matter how they try to tune the distance between the lenses, they always have such a strange pattern at the end. 就是当他们用那个透镜，然后还有直线光，然后再分析说这个透镜的效果好不好的时候，不管怎么样，它的那个影像里面就是会这样一圈一圈一圈一圈的，这很烦人，你知道吗？就是你现在在看一个土星，可是你的土星看到的光线却是这样一圈一圈糊糊的，还会分散，然后它就很糊，你就什么都看不到。然后这件事情在我们现代的显微镜跟现代的望远镜还会有就是这是一个你没有办法逃脱的现象，因为这个是光的本性。光的本性它就是会这样子，只要你把你那个波嘛，你把它聚焦到某一个程度，它们只要一产生，你只要刚好 match 到绕射跟干涉的条件，你就会看到那一圈圈。那这位意大利的科学家honestly, I don't know how to pronounce it, Grimadi. Grimadi, he just discovered that kind of ripple-like pattern, and then he thought it looks very much like the ripples on the water. So he just linked it to his experiences with fluid, and then he just gave it a name, like diffraction. Okay, and you can see that when you are working with lenses, and because light with different colors, they are working at different speed, so actually they have different focus lengths. So this is red light, green light, blue light. When they get focused, the focusing point is different, and it looks like this in your images. It's like the colors look blue and yellow and green and red, and they are somehow shifted in your images. And if you are using microscope made of low quality lenses, and then you can see that kind of effect too. And the way to overcome it is like we have the lenses like that, and then we just make another lens like this, and then catch it at the back of your lens, and then you can just somehow correct. It's like it focuses and then it diffracts it, and then you can just try to regulate the focus length of the two lenses, and then you can try to put all the colors together. So you can see here are the images. This is the images where the colors got dispersed and then various colors are shifted. And this is the image when you use the correction tool, and then you put the RGBs back together, and then you can see a very clear image like this. 好，所以这算是小小岔题啦，但我觉得这个还蛮有趣的。以后大家渐渐是用显微镜的时候，你也会发现这件事情，就是有一些显微镜的透镜，如果说它没有调好的话，它的你在眼前看到的影像会分裂成 RGB 3个颜色，不见得是 RGB， 有时候它也会分裂成更多颜色。那的状况，它就会变成你的影像看起来就是这样子糊糊雾雾的，然后呢，你那个圈圈好像一圈一圈的，然后有很多颜色会散开。那这个在影像分析上面很烦人，就是你就看不清楚然后你也搞不清楚那个颜色是哪里来的。那如果说你在你的凸透镜后面再加一个凹透镜，它的作用就有一点像是说，我先把我的光聚焦一点点，然后再让它们稍微散开一点点，就或多或少啦，你可以把它调整成好像全部都是直线，然后让它们可以在同一个点聚焦。然后这时候呢，你的 RGB 混色之后，你得到的影像就会更接近真实。然后呢，你有很多细节都会变得更加的清楚。好，所以这个是显微镜、单眼相机、镜头，就有一些我觉得有些人蛮狂的，他就会去买一个什么尼康的一个镜头，然后把镜头用锯子这样对切一半，然后想要看里面的镜片。我有放灯吗？我把那个拿掉了。好，大家可以自己去上网去 Google， 你会看到那个单眼相机的镜头啊，然后你看它那么大一个，对不对？它其实里面有很多个玻璃镜片，就是一堆凸透镜跟凹透镜的组合，因为它要做这件事情。它要做这个，一个是颜色的校正，还有一个是那个我等一下忘了那个叫什么，球面，球就是有的时候你的影像会中间凸起来4个角凹下去，就是他们也要用一些光学上面的透镜组合去做这样子的 correction。我搜寻一下好了，应该可以找到，因为那个蛮惊人的，所以我很喜欢在这个时候看这件事情。好，好像是Leica吧，Leica lens cross section， 这个 like this。So this is I think this is just okay. This is not a very impressive one. Okay. So I think this is a compact lens, but you can see here are different kind of shapes, and it's just correcting the colors and correcting the aberration. Oh, that is a very hard word. Aberration 就是变形。So, and here is a little lens made by Leica. Okay, and this is a little one like this, and then you can just tune it. This is for a street snapshot. 街拍，这应该是街拍镜，就是那种小小的摄影机。And here is and this one. I'm sure this one is variable focus lens. 就是这个应该是变焦镜头， 因为这一大段显然是你的镜头可以变长变短。我有看过一个很微的 ，and this one is delicate. So I'm sure this one is the most expensive one. We have many different kind of lenses and they are stacked together. And maybe we should look at Nikon. Nikon. Here is a quarter cut. So can look at it like that. Or a Zeiss. OK， 好吧，今天刚好都没有看到很厉害的。之前上课的时候，我有找到一个那个镜片，真的塞得满满的，然后都觉得哇，那个工程师怎么这么厉害？好，有兴趣的同学可以自己回去研究。好，那如果说你上完课之后，你发现你很喜欢光学的话，其实我还蛮鼓励你往这个方向发展的。我会觉得做光学镜头，然后做那种高品质的影像，我觉得这个工作真的是比做晶圆有趣多了。So if you learn optics and then if you feel like yourself, you're very, very interested in optics, and I really encourage you to work in optics, like high quality lenses and high quality cameras. I'm sure this is much better than being an engineer in TSMC, really. 好。然后对摄影有兴趣的同学啊，我非常鼓励你们去看一下那个。So for those students who are very somehow start to get interested in photography, I really encourage you to look at the histories of lenses companies like here are I just write it down. Here are good ones. Leica is at the top quarter. 徕卡镜头是最棒的、最顶级的。然后 Zeiss is very famous of their artistic images， 就是蔡司的镜头，他们创造出来的那个影像很特殊，就是它非常的有艺术感。然后还有另外是 Leica Zeiss， 还有一家叫什么？对 Leica is very known of the sharp images, so this is very realistic, and somehow because there are too many details in it, makes you feel like a little bit too very stressful. And Zeiss is soft and very, I would say it's very feminine. So I am a Zeiss fan actually, and but they are very expensive. So usually we use Japanese companies like Nikon. Nikon is more or less in the direction of Leica, and Canon is more or less in the direction of Zeiss. And here are some other ones like Fujitsu. Fujitsu is good, and some others. 还有另外一个 Olympus， 对 Olympus 好像也不错。但总之呢，你的摄影大概就是这4家镜头，然后他们的风格一种是比较接近锐利的，然后另外有一个是比较接近那种柔和，但是前后主体跟背景很清楚的会分出来的那种，那个是比较走蔡司镜头的风格。我们实验室的显微镜都是蔡司的，对，因为我觉得蔡司的影像比较接近明星是，通常啊。做光学的人会用徕卡，或者会用徕卡，然后呢，做生物相关应用的人会用蔡司，因为生物大部分是那种软物质，然后软物质它都会有一个非常特殊的3D 结构，那我们就会觉得比较喜欢用蔡司的镜头，因为蔡司它的对焦很结实，但是它可以把前后景很明显的区分出来。如果用徕卡的话，你常会有一种那个画面 很 busy， 就是很忙的，然后塞满各种资讯，看不到重点的感觉。但是如果是做一些那种光学元件的，他们就会觉得，比方说显微镜它的镜头它可能就会有尼康的，然后或是再好一点，它就会用徕卡的。好 ，OK， 有兴趣的可以去看，我会觉得这是一个很好的，你可以发展一些兴趣的方向。因为我们现在都是用。So nowadays we're using the smartphone and you're taking pictures and then you use the filter and then to change the colors into something that you want and show the mood so digitally. And I really encourage you to get into those true photography and those dedicated images inside, and I think it's really better than playing with the figures. 我觉得像现在我们大部分的那个摄影嘛，因为你的 smartphone 真的太方便了，然后又有很多修图软体，有没有？比方说 Instagram， 然后你拍张照片，你就可以选各种不同的景，然后展现出你想要表现的感觉跟心情嘛。我其实也蛮喜欢用这个的，我觉得其实不错，因为你用起来你没有负担啊，就是它是一种街拍抓拍，然后轻松写意的精神，其实这是很好的。但是我其实相信哦，如果你真的很喜欢摄影的话，你玩那个到一个地步，你就会觉得腻，对，就腻了。然后如果你开始觉得有点腻，就我非常推荐大家开始去了解这些古典的、专业的摄影的知识。对，我会觉得这是一个很好的兴趣，大家可以往这个方向发展。好 ，OK， 好，一堆闲话。Then okay, and then we'll come back. So we just introduced the lenses and we introduced how diffraction was discovered, and this is the diffraction on the microscope, and that was already known by Hooke because Hooke is very good at producing microscope and he's using his microscope to look at everything. He just made records on the structure of the fibers in plants and different kind of little creatures in the water. And when he was preparing his samples, and he just realized that the light creates such a colorful patterns there. And then just under the microscope, even if he is not looking at anything, but he just in his images he always see the colorful rings like that. And the colorful rings is just a combination of this one and this one. You can imagine in your head. 所以虎克在他的显微镜底下，他老是会看到这种东西，就蛮烦的。然后他就一直想要把它消除。然后大家看到这个彩色的一圈一圈，然后还有就是彩色嘛，还有一圈一圈，一圈一圈呢就是绕射，彩色呢就是这个现象。对，你可以在脑子里面想象一下，然后把这两个现象结合起来，你就原来如此。好 ，So Huygens and Hooke. Okay, and this is Huygens. And Huygens was looking for Saturn. 就是惠更斯他的正业其实是寻找土星，然后观察土星的土星环。And this is his notebook. This is originally when the telescope is not in a very good resolution, and when he is looking at Saturn, and he just discovered that he's the images that he got. So from the distribution of the two spots, and then you find it so interesting. He just find out, maybe Saturn has somehow the rings around it, and the ring is with respect to the Earth. And when you're looking at the Saturn, and somehow the ring is sometimes like that, sometimes like this. Seems like the ring is changing its angle. And then he just record everything, and then he just try to find the relation between his images and the tilting angle and the Saturn. So that was his original research. 所以惠更斯他当初他在做的研究，就是他看这些望远镜底下土星的影像，然后他推测出来，他觉得土星应该是有游泳圈，然后那个游泳圈呢有歪一边，然后土星它就是会绕着地球公转，所以他就从那个游泳圈的那个形状。他去判断说，我觉得土星应该是歪了几度， 他做的研究是类似这种，所以总之他是一个操作望远镜操作的很熟悉的人。So as a additional skill, and he is very good at operating the telescope. This is his telescope. This is how they try to avoid the iridescence, and this is how they try to avoid the colorful aberration. So this is his telescope. And in his notebook of his telescope technique, and people just discovered how he was thinking about how light is propagating in his lenses as a form of wave. And we just watch a video and see the explanation in a video. I think it's better. 我们看那个惠更斯的想法，我们用 video 看比较清楚，因为那个要动，
对于正统教育所教授的想法感到非常不可思议。所有的人跟所有的学校都。
As a source of secondary disturbance. The secondary wavelets emanate. A small pebble dropped in a pool of still water creates ripples on the surface. These ripples form concentric circular rings around the source of disturbance and spread outward along the surface. When these ripples reach a point on the surface of water, the point starts oscillating up and down. Different points, which are at the same distance from the source of the disturbance, oscillate in phase. That means all these points reach the crest or trough at the same time. The locus of all such points having the same phase of oscillation is called a wavefront. In case of water waves on the surface of water, we observe circular wavefronts. Each circular wavefront is a locus of all points having the same phase of oscillation.
好，这里我用中文解说一遍。就我们的那个波，我们现在是在处理一个球面波，然后那个球面波它在往前传播的时候呢，只要我们可以开始用相位来想这件事情了，就是你的波是这样震荡嘛，然后相位就是从0到2拍。然后如果说你的波上面相位完全一样的地方，我们现在就挑那个相位我们就挑那个 amplitude 最高的地方。然后呢，这一圈所有的波，它的相位都是一样的。那我们可以在这里，我们可以给它画一条界限，然后我们定义这个叫波前，就是那个波在一直往前传播的时候，我就选定这个相位是我的波的最前面。然后呢，我就盯着这个波前看，然后看它是怎么往前传递的。Okay, this is a definition of wavefront.
The propagation of the waves can be understood by studying the propagation of wavefronts. An outward normal drawn at any point on the wavefront represents the direction of the wave at that point. In terms of energy, we say that the energy of the wave propagates in a direction perpendicular to the wavefront. The speed at which a wavefront travels is the speed of the wave. Waves on the surface of water are two-dimensional, and hence the wavefronts are circular in shape. But the waves from a source of sound or a source of light in a homogeneous medium spread in all directions and are three-dimensional in nature. Now consider a point source of light placed in a homogeneous and isotropic medium, emitting light waves in different directions. If the medium is homogeneous, the speed of light waves is the same throughout the medium, and if it is isotropic, it is the same in all directions. The loci of all points, which have the same amplitude and vibrate in the same phase, forms a sphere with its center at the source of light. Hence, a spherical wave front is generated when a point light source is placed in a homogeneous medium. At a large distance from the source, These spherical wavefronts have large radii of curvatures. A small portion of a spherical wavefront at a very large distance from the source can be treated as a plane wavefront. In physical optics, we visualize light as waves and wavefronts. In ray optics, we visualize light as rays. A light drawn perpendicular to the wavefront in the direction of its propagation is treated as the ray of light in ray optics. Note that a wavefront is a surface of constant phase. If a particular wavefront is a locus of points with maximum amplitude, it continues to be like that as it propagates through the medium. Christian Huygens proposed a geometrical method known as the Huygens principle for finding the shape and location of a wavefront at some instant from the knowledge of the shape and location of the same wavefront at an earlier instance. According to Huygens' principle, each point of a wavefront is a source of a secondary disturbance and generates a spherical secondary wavelength. To understand Huygens' principle, let us now consider a primary wavefront AB propagating in a homogeneous medium. Then, according to the Huygens principle, each point of AB acts as a source of secondary disturbance. The secondary wavelets emanated from these points are spherical in shape and split in all directions at a speed equal to the speed of the wave. If the speed of the wave is v, then in time t, the radius of the spherical wavelets becomes vt. The tangential surface common to all these spheres in the forward direction gives the shape and location of the new wavefront after t seconds.
I think this picture is explained everything in a very good way. For the Huygens principle is actually a mathematical model. It's not really related to the physics itself, but it is just a method of thinking which helps you to explain how waves propagate. 就是大家要注意一件事情，就是惠更斯原则，它不是物理的原则，它只是一个，甚至连数学模型都称不上的东西，因为它里面有很多先入为主的假设没有经过验证，所以请大家要注意。但是它是一个很好用的思考模型或思考模式，对，所以就是大家在使用那个惠更斯原理的时候，就是你要放在心上的地方。So Huygens' principle is actually not a physics or even it's not qualified as a mathematical principle because it has many hypotheses which is not proved at all. So it's just something like Huygens just jump into a conclusion and think that, I think waves should propagate that way, but nobody can really do an experiment to prove it. So we cannot take the Huygens principle as a math or as a physics, but it's a good model for you to think about how those waves propagate in a complex shape waveform. And I think the way to explain it is really good in this picture because you can see that this is a spherical wave and we just pick all the wavefront. So this is wavefront, wavefront, wavefront. And you can think about them as just a wavefront getting far away, or you can cut the wavefront into small pieces, and you can just think that every small pieces of the wavefront is a point, and the point is just like a secondary point source, and it's emitting a secondary spherical wave too, just like bubbles lining up, and those bubbles are getting bigger. And those secondary spherical wavefronts are growing bigger in the same speed. So that's the reason why if you pick all of these spherical wavefronts, if you pick the front of them, and if you take a link between all of them, you can reconstruct the original wavefront by the little bubbles. So this is how Huygens is thinking about the propagation of wave. 所以我会觉得惠更斯 principle 它很有趣的地方，就是它会把一个球面波的 wavefront， 它把它想象成说上面你可以把它切割成一块，然后每一个一块都是一个小点，然后每一个小点都是一个新的球面波的源 source。然后呢，每一个小点它就是一个小的刺激的球面波，然后就是球面波1号、2号、3号、4号、5号，像一串肥皂泡连在一起一样。重点来了，重点在于说这些刺激球面波它长大的速度，每一颗都是一样多。那所以说，你如果想象我现在有一串泡泡，有很多的泡泡，那我就抓那个波前最前面的地方。每一个波前最前面的地方，其实就是像我一样的地方，你就把它连起来，你会发现你可以从一串小泡泡，你可以重建，就是原本的波前应该要走到哪里。所以它是一个我觉得它是一个非常图像化的傅里叶分析。This is a pictorial Fourier analysis, and this is, I think, that the model is built in a very interesting and very creative.
In the image, the surface A-B- represents the location of the wavefront AB after t seconds. The secondary wavelets must be directed backward as well as forward from the secondary point sources. If this would be correct, we would get a surface such as A'-B' as a back wave. But experimental results do not show the presence of any such back wave. In order to explain this, Huygens proposed that the intensity of the spherical wavelets is not uniform in all directions, but is maximum in the forward direction and 0 in the backward direction. Hence, the wavelets as well as the whole wave always propagate in the forward direction only.
And here comes the problem. I just explained it one more time. And here comes the problem. If every little point is just a secondary point source, and then the secondary waves or spherical waves are growing that way, and obviously those waves going to the backward direction, they will create another wavefront and cancel the other ones, right? And that never really happens in reality. And this is a really, this is the major weakness of Huygens' principle. And Huygens just explained that this is a model, and we are just looking at the wavelet as asymmetric objects. So one of the side is growing and the other side there is nothing. So I think this is the point why I said that I don't think the Huygens principle is mathematically proved, because in nature, if something is asymmetric, you must have a firm reason for it. But we don't have the reason here. But anyway, we can use this model and we can explain how wave is propagating in strange boundaries. So we just use it as a model, we just use it as a tool to think. 所以这边它比较麻烦的事情是说呢，你的点一个 point source， 然后你有一个 spherical wave 变大。但如果说你后面这边有就是往你波 propagate 的方向反方向过去，那你把这些波连在一起的时候，你会创造出另外一个 backward 的 wavefront 嘛？然后这个往后逆袭的波，它就会跟别人会相撞啊。然后应该就会乱掉，对吧？如果照现实状况来讲的话，可是我们在看那个水的涟漪的时候啊，我们没有看到这件事情，对吧？所以那惠更斯当然也知道他的模型这是他最大的弱点，这没有办法。对，那这就是为什么我在一开始说，我觉得惠更斯 principle 其实在数学上面，它甚至连一个数学模型都称不上。因为他没有告诉我们说，通常如果你在一个模型里面，你要用一个这种不对称、前后不对称的东西，你要有一个非常 非常确定的理由，你至少要有个理由跟大家说为什么会觉得我的 spherical wave 前后不对称。可是他这里没有办法提出一个理由，所以就是这是惠更斯 principle 一个非常大的弱点。可是因为它太好用了，对，因为惠更斯 principle 就是我们现在只有看球面波嘛。那如果说你的波有很多种奇怪的形状，惠更斯 principle 还是可以用的。那因为它真的太好用了，所以我们大家就先暂时对这个前后不对称的问题，我们先暂时放过它。好，所以这个是惠更斯 principle。And I know that there are many students who are very those students who are very careful and they will discover this problem by themselves. So I just explain it here. 就有一些比较细心的同学，其实他们自己在看书的时候就会发现这个问题。对，所以我就先跟你们解释一下，这个是非常 artificial 非常人为的一个理由。
Now let us use Huygens principle to find the location and shape of a plane wavefront at a later instant of time t. Let AB be the plane wavefront at time t equal to 0. According to Huygens principle, each point of AB acts as a source of secondary wavelets. The radii of these spheres will be Vt after t seconds. The plane touching these small spheres in the forward direction gives the shape and location of the new wavefront after t seconds.
This is Huygens principle. And this is Huygens principle for reflection. And so we can just, we start from a plane wave, and the plane wave is walking this way. This is air, and maybe this is plastic. Let's take it this way. And all of these plane wave, this is the wavefront of a plane wave, and each wavefront, I just simply take them as the source of the secondary wavelets. So this is source, and all of the point sources generate the secondary spherical waves. And here you can see that we are not really connecting it this way, but you can see that it's we connect it to the other wavefronts this way. And by reconstructing all these wavelets, and then you can create another plane wave in the new media, and then there is an angle between them. And this is again, you can do the reconstruction by assigning velocity air, velocity plastic, and by changing the ratio between them, and then you are actually changing the sizes of all of these wavelets, and that's why the angle changes here. 然后你用惠更斯 principle 处理折射的话，它的关键点就在于说，你在两个介质里面波的速度不一样，然后你的 wavelet 球面波往前传播出去的速度就会不一样。好，那你可以想象一下，就是如果说对，你可以稍微想象一下，你的速度变快或变慢的时候，它会怎么样影响你的 wavelet。但是最后的 principle 就是呢，你把这些 secondary wavelet 的波前全部连在一起，你可以重建一个平面波。那你退出来看，然后你只看进去的平面波跟出来的平面波的时候，你就会发现呢，这个平面波行进的方向转了一个角度。So this is how Huygens is explaining refraction by the little wavelets. How we decompose the plane wave into point sources. Point sources generate spherical wave, and reconstruction of the spherical wave gives you the output plane wave. Good. Very pictorial. Okay, and then here I just explain how Hagen's principle is working on diffraction. 这个是我们今天最后一个题目，解释一下我们要如何用惠更斯的原则思考 diffraction 这件事情。So we can take this is the slit, this is the fine slit, and when the plane wave, I should draw a plane wave here, sorry. When the plane wave is coming in, and let's just take two extreme cases. So here's a point closer to the upper bound, and here's a point closer to the lower bound. And the point source here is generating a secondary wavelet like this, and the point here is generating another spherical wavelet like that. And then let's look at the point where the phases are exactly the same. For example, here, let's just take the solid line is the top of the wave, and the dashed line is the valley, the bottom of the wave. 我们这边先把那个大家请先想象，你的实线是波峰，虚线是波谷 ，and let's look at the point where all the top are overlapping. 我们现在先来找，就是我们的波峰会叠在一起的地方。所以 and we just say here is one, here's another one. And if I just continue drawing my wavelets, and I can find some others here and here and here, and if I link them together, then I will have something like a chain of constructive interference. And here's another one, so I can see that this is the bottom point of my wave, and here's the two bottoms overlap. And if I link all of them together, and then I will find a line of constructive interference. And here is another change. Here's another point for the constructive interference, you can see. And here's another line for constructive interference, isn't it? Okay, so this is for the constructive part. And this is for the destructive part. So this is destructive if the positive part of the wave is overlapped with the negative part of the wave. 所以大家可以注意一下，如果有两个 wavelet 嘛，然后呢，在这里呢，那个波峰，如果它的波峰跟它的波谷刚好凑在一起的话，那你的波就消失了。所以那这就是 destructive 的 point。那我们来找 destructive 的 point 在哪里？ Let's look at the point of destructive interference. So this is destructive. You can see a top and a bottom somehow combined together. A top and a bottom, a top and a bottom. So this is destructive. A line of destruction. Here is another line of destruction. Yep. So you can think back to the water tank experiment, like this. So we just see the constructive and destructive interference, and somehow they can create a pattern like this. Okay, and then we'll put all of them together. So you can see that, if I take myself in a polar coordinate, so if I look at it in a polar coordinate, so at the center I have a constructive superposition, and then destructive and constructive. They are alternative. 所以大家可以想象，如果我把建设性的跟破坏性的干涉，我把它全部叠在一起，你就会发现，如果你在这里画一个极坐标，然后你这样扫描扫过去，你就会发现它是交替性的，就是有建设性、破坏性、建设性、破坏性、建设性、破坏性，它就是会这样子像循环一样一直出现。And then if we just take a screen, so we stop the light on the screen, and you can see that, wow, that's the reason why I have fringes pattern. So 所以大家就会发现，这就是为什么我用个平面我把它挡住的话， 你就会看到那个一条一条的条纹，亮的地方就是建设性干涉发生的地方，暗的地方就是破坏性干涉发生的地方。所以这就是为什么你最后在 diffraction 的时候呢，如果它是一个狭缝，一维狭缝的话，你在后面你就会看到它就分散成一堆光点，喷的到处都是。对，这个就是 diffraction pattern 产生的理由。And we just use the Huygens principle to explain why you see fringes why you see the diffraction pattern as the fringes if you're shining a light through a slit. Okay. Yep. How long does it take? 2 minutes. Let's watch this video and then we end our lecture here. 我们把这个影片看完，然后我们今天在这里下课。超过一点点时间，大家忍耐一下。大家就是记得那个影像，我们接下来会分析为什么那个影像会长那个样子。好，那我们今天就上课上到这边，感谢大家。So you can just remember how the double slit fringes are displayed, and we are going to analyze why it goes like that later. And the lecture today is up to you.